Welcome back to Barefoot Math. Our topic today is Arthur Engel's invention of the probabilistic abacus. When you hear the word abacus, you probably picture the Chinese-Japanese kind, with beads that slide on rods. But there are also older, more primitive abacuses, in which beads just get moved around on a board. No rods are involved. That's closer to the kind of abacus we'll be using today. Back in the 1970s, the German mathematician and computer scientist Arthur Engel was visiting the US and looking for a way to teach probability theory to fourth graders. He ended up creating something marvelous, a way to design custom abacuses that solve probability problems. I'm going to dive in and show you how to use Engel's method to answer a question that appeared in the blog 538 on September 9, 2016 as the week's Riddler puzzle. The problem was contributed by Bruce Torrance, a math professor at Randolph-Macon College. Lots of people solved the problem, but as far as I know, I'm the only person who solved it using Engel's method. Here's the problem, slightly rephrased. Eustace and four friends find a $100 bill on the floor, and they decide to award it randomly, winner take all. The five of them sit around a table and play a game in rounds. During each round, one of three things can happen, each of which has probability one-third. The bill can move one position clockwise, or the bill can move one position counterclockwise, or the game ends, and the person with the bill in front of him or her wins the money. What are the chances that Eustace wins the money if the bill starts out in front of him? Part of what makes the problem tricky is that we can't know ahead of time how long the game will last. It's incredibly unlikely that the game will last a million rounds, but it's possible, and we'll get the wrong answer if we neglect that ever so unlikely possibility. Nonetheless, the problem has a reasonable answer. It's 5/11ths, or just under a half. But how can we derive this answer? Let's build an abacus for Torrance's problem. There are 5 places the money can be on the table, and 5 people who can pocket the money, so we create an abacus with 10 spots on it. 5 inner spots representing where the money is on the table, the green one corresponding to the money being in front of Eustace. Ignore these chocolate chips for now. And 5 outer spots representing who takes the money home. The red one corresponds to Eustace taking the money home. We imagine a token, again, nothing to do with these chocolate chips, that represents the money, and a 3-sided die with sides marked clockwise, counterclockwise, and out, telling us where to move the token. If you don't have a 3-sided die, and I don't, just use a 6-sided die that has 2 faces marked clockwise, 2 marked counterclockwise, and 2 marked out. If the die is fair, then this is the same process as the one Professor Torrance describes, and the question he's asking is, if the token starts out on the green inner spot, what's the chance that it ends up on the red outer spot? Here comes Engel's stroke of brilliance. Let's keep this board, but change the rules. We'll use lots of tokens, which we'll now call chips. Mine will be chocolate, and we'll impose a rule for moving the chips around. As soon as the spot in the inner ring has 3 or more chips, we slide one of the chips clockwise, one of the chips counterclockwise, and one of the chips out to the outer ring. The operation of sliding away 3 chips is an example of what mathematicians call chip firing. Now that we've built Engel's device, we have to initialize it the right way. I've already done this. We load each spot in the inner ring with as many chips as we can without causing any chip firing to happen. That means we put 2 chips on each of the 5 inner spots because a third chip would cause that chip to fire. This configuration, with 2 chips on each of the inner spots, is called the maximal stable loading, or the critical loading. Now the actual computation can start. It's a bit like swine in a line, except it's for only one player, and the player has no freedom of choice at all about where to add a chip, and chips fire in threesomes instead of pairs. And the arrangement is not a line, but a circle. On each move, we add a chip at the green spot, and then we do chip firing operations until we can't do any more chip firing. And then we add another chip at the green spot, and then do more chip firing operations until we can't do any more chip firing, and so on, until, at some point, we recognize that we're back at the maximal stable loading of the 5 inner spots, 2 chips at each spot. When that happens, the distribution of the chips on the 5 outer spots tells us exactly how likely it is that a given person gets to take the $100 bill home. So let's see it. Add a chip at the green spot. Now there are 3 chips there, so we send 1 to each of the neighbors, and 1 goes out. But now there's 3 chips over there, so send 1 of them out, and 1 of them to each of the neighbors. And there's 3 chips over there, so send 1 of them out, and 1 to each of the neighbors. And there's 3 chips there, so send 1 of them out and 1 to each of the neighbors. And now there's 4 chips there, so send 1 of them out and 1 to each of the neighbors. And now no more firing can happen because none of the 5 inner spots have 3 or more chips on them. So what do? Add another chip on the green spot. Hey, we've got 3 chips, so send 1 of them out and 1 to each of the inner circle neighbors of the green spot. Can we do any more firing? No, not yet. So add another chip here. Can we do any firing? Nope. Can we do any firing? Nope. Can we do any firing? Yes, we can. So send one chip out and one to each of the neighbors. Can we do any firing? Yes, we can. One chip goes out and we send one to each of the neighbors. And likewise over here, one chip goes out and one goes to each of the neighbors. And now no more firing can happen at this point. So it's time to add another chip at the green spot. There's three. We send one out and one to each of the neighbors. And now no more firing can happen until we add one, two, three chips, and then one chip goes out and one chip goes to each of the neighbors. No more firing can happen, so we add another chip here and another chip here. And oh wait, look, we're back at the original critical loading. Each of the inner spots has two chips on it. So we stop the computation and we read off the answer to the original problem. There are 11 chips in the outer ring. And of those 11, exactly 5 are on the red spot. So the answer to Torrance's problem, according to the abacus method, is the fraction 5/11ths. Eustace has a 5 out of 11 chance of being the one to keep the $100 bill. What's more, each of Eustace's neighbors has a 2 out of 11 chance, and each of his non-neighbors has a 1 out of 11 chance. I said that Engel came up with this method when he was teaching probability theory to fourth graders. The usual way of doing problems like this involves adding and multiplying fractions, which most fourth graders aren't comfortable with, or worse, simultaneous systems of linear equations, which most fourth graders haven't even heard of. There's even a calculus method for solving problems like this using infinite series computations. Engel's abacus method doesn't involve anything more complicated than moving chips around and at the end writing down two whole numbers with a slash between them. This method works for many problems. Next time, I'll apply it to some much simpler problems so you can see a curious relationship between Engel's probability abacuses and the more traditional kind of abacuses that were introduced for recording and manipulating numbers. Now, I haven't told you why this abacus method works. If you're the kind of person who doesn't like to use a tool without knowing how it does its magic, my Mathematical Enchantments essay for the month of August will include some links that may interest you. But even without knowing why the probabilistic abacus works, I hope you'll agree that it's a tasty way to solve problems in discrete probability theory.